I wanted to spend just a few minutes talking about sampling distributions because of their importance in understanding how we make inferences. The book is not entirely clear on what sampling error is. I want to talk about a simple example that might clarify it. For the sake of this example, imagine that we know the true population age is 52 in Canada. Let's say I take a sample of 1,000 Canadians and calculate the average. I almost certainly will not find that it is 52. Maybe I calculate the sample average to be 54. Sampling error is the difference between what I calculate in the sample and what the true population value is. Note, this is a theoretical idea because we rarely, if ever, know the true population value in real data problems. The sampling distribution is a distribution of sample statistics. The book calls this the sample distribution, but I think that terminology could be a bit confusing. The frequentist thought experiment that motivates the way we make inferences relies on our ability, theoretically, to take many samples from the population of size n. In our example, we could imagine that we had not just one sample of 1,000 Canadians, but let's say we had 1,000 independent samples of 1,000 Canadians. The central limit theorem tells us that if we calculated the average age in each of those 1,000 samples, that the distribution of those average ages will be normal, with a mean equal to the true population mean, and standard deviation equal to the standard deviation of age in the population divided by the square root of the sample size, 1,000 in this case. This latter quantity, the standard deviation of the distribution, is called the standard error. This distribution is called the sampling distribution. It tells us how sample statistics are distributed. Note that this is a purely theoretical distribution because it depends on population characteristics that we will not know. We do know that this result, the normality of the distribution, holds in the following cases. When the population distribution is normal for any sample size. When sample size is sufficiently large, some references say 30, others say 120, regardless of the shape of the population distribution. Here's a little simulation to show you how it works. The histogram on the right shows the distribution of sample means from 10,000 independent samples from the population. Here we can control the sample size and the population distribution. Note that if we maintain normality of the population distribution and reduce the sample size to around 10, we still get what looks like a normal distribution. If, however, we switch to a chi-squared distribution, which is heavily skewed to the right, we get a sampling distribution that is also skewed to the right. If we increase sample size to around 30, you'll see that we start approaching something that looks more normal, though we may still get a bit of a right skew. Switching to a uniform distribution, one where every value gets equal probability, and switching our sample size to 10, we have a distribution that looks symmetric, but is a bit flatter in the middle than we would expect from a normal distribution. There's a name for distributions that have this probability of being flatter in the middle than they might otherwise be. They're called leptokurtic. Now you can impress your friends with some fancy statistics lingo. There's no quiz at the end of this video. I just wanted to make sure you understand what a sampling distribution is, because we're going to refer to this lots and lots of times in what's to come.